All right, so we left off on example 11.3, and we were going to compare this force exerted against the dam with the weight of water in the dam. And we previously, in example 11.1, as it states here, found the mass of this body of water, this reservoir, and that mass was right here, 2 times 10 to the 12, okay? Okay, and so that's our mass. So we put 2 times 10 to the 12th here, kilograms, and gravity, G, oops, can't quite fit it. So we have 2 times 10 to the 12 kilograms times 9.8 meters per second squared. And so our force will be 1.96 times 10 to the 13th newtons. Okay, so this is the weight of the water versus that force being exerted. Okay, and so you can see the difference, which one's higher than the other. Okay, this is 10 to the 10th, this is 10 to the 13th. Okay, so it's not exerting the same amount of force that the water weighs. Okay? All right. So moving on to atmospheric pressure. This is the pressure due to the weight of air above a given height. Okay, so this is very similar to what we were just looking at with fluids, okay, but we're calling this atmospheric pressure. Okay, and the average pressure at sea level is what we call 1 atmosphere, or 1 ATM, okay, and this is also 1.01 times 10 to the 5th Newton per meter squared, or 101 kilopascals. Okay, so again, if we're looking at a diagram of this, we're saying for 1 square meter, okay, at some height, okay, or, well, the height would be sea level, so we're saying this is sea level, okay, that the weight of this is going to be 1.01 times 10 to the 5th newtons. Okay, so the weight of this air, you could say, is going to be that. And so our pressure is that weight, or that force, over our area, which is 1 meter squared. Okay, so atmospheric pressure. So let's understand this a bit more using example 11.4. Calculate the average density of the atmosphere, given that it extends to an altitude of 120 kilometers, and compare this with the density, with that of air, 1.29 kilogram per meters cubed. Okay, so the average density of the atmosphere. Okay, so let's go back and remember that pressure equals H rho G. Pressure equals H rho G. Okay, we just said that our pressure, our average pressure, is going to be 1.01 times 10 to the 5th. So our pressure is 1.01 times 10 to the 5th, and this is in newtons per meter squared, or pascals. Okay, and so using this equation, we can solve for our density. That's going to be our pressure over H times G. Okay, so our pressure is 1.01 times 10 to the 5th pascals over our height, which is 120 kilometers. Okay, so that altitude, or that height, we're going to need to turn into meters. So let's go ahead and do that. So 120 times 1,000 is going to be 1.2 times 10 to the 5th meters. So 1.2 times 10 to the 5th meters. And then we have gravity, which is 9.8 meters per second squared. Okay, so taking that 1.01 times 10 to the 5th divided by answer times 9.8, we get our density of 0.0859, okay, and this was newtons per meter squared. Density is in kilograms per meters cubed. Okay, so this is our density of the atmosphere. Okay, and so if we want to compare that with the density of just air, okay, we can see that it's much less. Okay, so air is greater than density of the atmosphere. Okay, and that's most likely because air has different molecules in it. Okay, and the atmosphere gets thinner. Okay, so this is the idea, okay, that we're going after. Okay, let's move on to example 11.5. Calculate the depth below the surface of water at which the pressure due to the weight of the water equals 1 atmosphere. Okay, so what depth do we need to be at for the pressure to be equal to 1 atmosphere? So pressure, again, is H, density times gravity. Now the density of water, what was the density of water? I believe we used it before. Yes. Okay, it's 1 times 10 to the 3rd. So, density of water, 1 times 10 to the 3rd kilogram meters per cubed. Okay, and so we want to know the depth, so that's going to be H. So H equals pressure over, sorry about that, density times gravity, acceleration due to gravity. So our pressure is 1 atmosphere, okay, or we'll need to convert that. So 1 atmosphere is just going to be 1.01 times 10 to the 5th, like we used in our last example, 10 to the 5th, and this is in Newton per meter squared. Okay, so then we have our density, 1 times 10 to the 3rd kilogram per meters cubed, and our acceleration due to gravity, meters per second squared. Okay, so we can put that into our calculator as well. 10 to the 3rd times 9.8, and we get our height, or our depth. Our depth below the surface is going to be 10.3 meters. Okay, so this is at what depth below water we would need to be to get that same pressure. Okay? Alright. So we're going to move on now to an idea called Pascal's principle. Okay? And it states that a change in pressure applied to an enclosed fluid is transmitted undiminished to all portions of the fluid and to the walls of its container. Okay? This implies that the total pressure in a fluid is the sum of all pressures, is the sum of the pressures from different sources. Okay, so if we apply a force, say in this figure, apply a force to this side I'm going to say side 1 and side 2. So if we apply a force to this side of this little chamber, okay, then we should have the same amount of pressure, I guess, build up on this other side. Okay, so this really is just a way of saying the pressure should be equal throughout a system. Okay, the total pressure should be equal. And so, because of that, we can also say that the force of the first little area here over the area is going to be equal to the force over the area over here. Okay, so they're proportional, right? They are related to each other through this. Okay, so this is Pascal's principle. Okay, so again, if I apply a force here, there's going to be a force that kind of in response to that other one that was applied, if that makes sense. Okay, I know that was kind of a little bit confusing to understand, but we'll go through some examples and then it should be okay. Okay, so let's go ahead and do that. We're going to start with example 11.6. Okay, we have a force of 100 newtons, and that is applied to a brake pedal. Okay, and this acts as a pedal cylinder called the master through a lever. A force of 500 newtons is then exerted on the pedal cylinder. Okay, and there's pressure created in the pedal cylinder, and it's transmitted to 4 wheel cylinders. Okay, the pedal cylinder has a diameter of 0.5 centimeters, and each wheel cylinder has a diameter of 2.5 centimeters. So we want to know the force, calculate the force F2 that's created at each of the wheel cylinders. Okay. So again, we have one force, F1, or not F1, that is applied to the brake pedal here. Okay. Then we have some F1 and then some F2, and we need to figure out what F2 is. Okay. So what we'll do is we'll apply the last idea, Pascal's principle, to this system. Okay. So again, the first pressure should equal the second pressure. So P1 should equal P2. Okay. Or the force 1 over some area should equal F2 over some area. Okay. And this question, again, let me just state it again. We have a force applied by this person on the brake pedal, and that force in turn turns into another force, F1. Okay, and that's what this 500 newtons is. Okay, that's then applied to the system, okay, over our area. So we're trying to find F2. F2 is going to be F1 over A1 times A2. Okay, so we can plug our values in. F1 is 500 newtons. We have our area of 1. That's going to be, remember these are cylinders, so we're going to say pi r squared. Okay, so our area is going to be pi r squared. So our r is 0.5 centimeters. So we're going to have to convert that. And I'm running out of time again. We will continue this in the next video.